This work was done in collaboration with my colleague Abram Clemens and my co-advisors Saurabh Bagchi and Matthias Peyer. So I would like to start this talk with an interesting puzzle that had a surprising answer, at least to myself. And it goes like this. What can be the common thread between an exploit allowing attackers to gain control of a smartphone even without any user interaction, to exploits allowing attackers to gain control of a host system on a vehicle or even control it in driving mode, to attacks on industrial control systems that cause economic and physical damage? And the surprising answer is that while these are complex attacks with multiple steps, they have one common target, which is embedded in IoT devices running microcontroller systems. And so the common perception is that these devices are standalone devices like your smart door lock, but they can be the Wi-Fi system on a chip on your smartphone, they can be the engine control unit gateway on a vehicle, and they can be the controller on an ICS. The second part of the story, which is the type of attack, which you probably guessed, is the type of attack is a control flow hijacking attack, which gains arbitrary execution over the device. And so one common question is that why are attackers using MCUs or microcontrollers as the weak link, jeopardizing the security of the entire system? The reason is that these systems are different from general desktop systems. So I'll just compare them to what we have on a desktop system. So what you see on the left is the memory layout of an application for a desktop system, and on the right, the memory layout application of MCUs. And I'll refer to microcontrollers for the remainder of the talk as MCUs. And so on a desktop system, you have very large virtual memory in gigabytes, but on MCUs, you have very small memory, which has physical memory. So at most, a couple of megabytes of flash and 100 kilobytes of RAM. This comes into play if we talk about a standard defense like address space layout randomization. So usually when you run an application on a desktop system, the address is randomized each run. That reduces the probability of an attack. However, on MCUs, well, we have physical addressing. That's not going to change. And even if we do randomization, this has very low entropy. And so basic defenses that we have are not going to be applicable with the same guarantees on MCUs. Even if we reset the device, the same layout is going to be the same for MCUs. However, one advantage is that since we have small memory, is that we're going to have smaller code for MCUs. And so more powerful analysis that might not be applicable to large code bases on desktops can be used for MCUs. The last difference is data execution prevention, which is a standard defense for desktop systems. Because of bad security practices, these are usually disabled on MCUs. But this is fixable. We can use the memory protection unit to enable DEP. But the other, or the previous mentioned problems are inherent to MCUs. So we need something different. And so for this talk, we focus on return addresses because they are more prevalent and they are more historically more preferable target for attacks. For forward edges, we can use CFI, but here for return addresses, we need a different mechanism. And so conceptually, let's see the defenses that we have and how do they map for MCUs. And so here on this graph, you see on the y-axis, the runtime overhead. And on the x-axis, you see the security. And let's choose 10% as a cutoff between low and high for runtime overhead. And we're going to categorize each security mechanism into three categories: using the return address, the location of the return address, and the integrity of the return address. And we would like the mechanism that we're going to come up with to be without special hardware. Remember that these are defense mechanisms, or these are devices that are constrained. So assuming that you have a trusted execution environment is not going to be applicable here. Most of the deployed devices do not have a trusted execution environment, or T. And so if we map out conceptually the defenses that we have, for example, control flow integrity on the bottom or shadow stack on the top, the ones that you see with the green circles do not require special hardware. But the ones with orange circles require special hardware. For example, shadow stack requires T, or trusted execution environment. The issue here is that the ones on the left have limited security guarantees. For example, CFI, the attacker can still corrupt the return address. We only just limit how the attacker can use it. For example, limit the possible target set to a reduced one. For location, like randomization defenses, we just hide the location of the return address, but it's still writable. The attack can still happen. For integrity, we fully protect the return address, but the issue is that these defenses, for example, like a shadow stack, have high runtime overhead on MCUs, and they require special hardware. So ideally, you would like something to have return address integrity. It will prevent the attack. It will also be practical. It will have low runtime overhead, and it will not require special hardware. And this is our contribution, µRAI, that will combine all these features into one package. This is, again, the same graph with the related work, but I'm not going to go to details for the sake of time. And again, the high-level point here is that µRAI is the first to combine these three features. And so at the core of µRAI, at the core contribution here, is something we call the return address integrity property. So every control flow hijacking attack starts by one step. That is, the attacker corrupts the return address by overwriting it. And so the main limitation of the defenses that we just laid out is that they do not prevent that from happening. Rather, they just deal with the artifact. For example, information hiding, you just hide the location, but once the information is disclosed, everything falls out. And so the key solution is not to deal with the artifact, but we want to prevent the possibility of overriding the return address from ever happening. And for this, we propose the return address integrity property, which is defined as the following. We ensure every return address is never writable except by an authorized instruction. And second, return addresses are never pushed to a stack or any writable memory. This stands against the common notion that we're going to push to the stack or pop to the stack. We're going to have an alternate mechanism that changes this, the stack mechanism, basically. And so before I go to the low-level details of µRAI, I'll introduce the threat model and what are the high-level protections for µRAI. And so we assume a powerful attacker. The attacker can read from anywhere to memory. The attacker can read anywhere to memory. And the attacker knows the code layout, even the current instance of the firmware. So there is nothing hidden in here. And the attacker, for our purposes, targets the backward edge, since we are protecting the return addresses. And so what you see here on the left is a sample call graph of an application. And on the top, you see functions executing without privileges. On the bottom, the functions executing in privilege mode. So in both domains, the attacker can corrupt the return address, for example, for a code reuse attack. But in the privilege domain, the attacker has an alternative vector to use, which is sensitive memory mapped I/O. An example is the memory protection unit that enforces read, write, and execute. So, for example, if we use the MPU for dep, then the attacker alternatively can just disable this MPU, allowing code injection and replacing the firmware. And so what µRAI does is that we have first one mechanism we call state register encoding. This is going to prevent the attacker from ever corrupting the return address. However, notice that the yellow parallelogram there, the sensitive memory mapped I/O, is still open. And so for that, we introduce another thing, which is software fault isolation, to protect the sensitive memory mapped I/O. Notice that we only enforce software fault isolation for the functions executing in privilege. So these are a limited number, so we have efficient and low runtime overhead. And so how does µRAI basically enforces these mechanisms? This is the high-level achievements or goals of µRAI. So first, we enforce the return address integrity property. We protect exception handlers. And we ensure that this is secure also and is practical with low runtime overhead. So in order to ensure the return address integrity property, remember, we're not going to use pushing and popping to the stack, but rather we use a state register and a read and a jump table and read and execute all the memory. So what exactly is the state register? It's not any special hardware. It can be any general purpose register. With a one caveat, we have the following conditions. First, it's only used by µRAI. Second, it's never spelled, so it cannot be overwritten through a memory corruption. And third, it does not contain the return address, but rather an encoded value. So how does this actually work? Consider the following call graph on the bottom, and each edge here is a call. And so what we want to see here is that function 2 on the far right has two call sites. And how do we find this call site? And so what's going to happen with the state register adhering to the condition we just mentioned is that the state register, if we go through the top edge or the orange one, somehow it's going to change to 1. If it goes to the lower or bottom edge, or the green one, it's going to change to 2. And what function 2 basically does is that it's going to read the state register and it's going to know its call site. This is good in theory, but how do we actually encode that state register? And the answer is we encode it using an XOR chain. So I'll go through how this works actually, and this is the key point here. And so here you see again function 1 calling function 2 through 2 call sites. And on the top of that, you see the state register. So the state register is a 32-bit register, and it's divided in two parts. First is for recursive calls, the second for encoded or normal calls. I'm going to leave the recursive ones. The details are in the paper. I'm just going to discuss the normal ones. And so we initialized it to C. The first step we're going to do is that we're going to instrument each call site with an XOR before it and after it. And what this does is it's going to encode the state register before, it's going to decode the state register. And this XOR is with hard-coded keys, which we call function keys. These are in code and read and execute, so they're not corruptible. The second step is we append a jump table in each function. And this jump table is basically a list of direct jumps. And these jump tables are basically the targets, the return targets of each function. So we use static analysis to get the possible call sites. And what we do, we give a unique ID for each possible return target or for each possible call site. We call these function IDs, and they are the possible values of our state register here above. And so we just match what's the current state register value and going to execute the direct jump associated with it. And basically, the combination or the list of jump tables and unique IDs we call the function lookup table. So let's go through this example step by step and see what's going to happen. And so first, function one is going to call function 2. The first step is that we're going to encode the state register. So we're going to XOR C with key 1, and we're going to call function 2. Two things are going to change. On the top, C, the state register is going to be C XOR key 1, and now function 2 wants to return. And so it says, OK, what's the current value of the state register? I'm going to execute the direct jump associated with that value. And so what you can see is C XOR key 1, and the direct jump associated with it is function 1, 1. And what do you know? This is actually the correct return location. But when we return, we have another XOR. And the key thing about XOR is that it's the inverse of itself. So when we XOR again, we actually retrieve the state register value, C. The same goes for other calls. And so we basically can call and return as the same as push and pop to the stack. But the key difference is that nothing is ever put on writable memory. And so it's not corruptible by an attacker. So OK, we protected the return address. Now, how are we going to protect exception handlers or privileged execution? And so what you see here on the right, another call graph. And on the far right, you see the rectangular exception handler. And the problem here is that if we have the vulnerability in privileged execution, the attacker might say, oh, OK, I'm not going to corrupt the return address, the state register. I cannot corrupt the jump table. Instead, I'm just going to disable the NPU, therefore allowing code injection and just changing that jump table that you assumed is in read and execute only memory. Note that these sensitive memory mapped I/O we cannot put in readable memory because of the limitation of the architectures. And so what we do is that we enforce software fault isolation, but only on the functions, the exception handlers and function called by exception handlers. And the key here is that we only protect these limited number of functions, therefore we have low runtime overhead. What we do is that we basically, for every store instruction the attacker might use, we make sure that this does not point to the sensitive memory mapped I/O, like the NPU or others. The details for the other regions are in the paper. And so we have a secure design. How do we actually make this efficient? And so what you see here is function 1, and the correct return location is 4. Which is the fourth index in the jump table, if you can't see it. And so if you remember, if we wanted to look up this target, which we call the target lookup routine, we said, OK, the function is just going to see what's the value of the state register and we return. But if we have a long table, this can be possibly slow. So what we do is that we insert a relative jump before each function lookup table or jump table. And we use the state register as an index into this jump table. And so using this relative jump, we basically have this relative jump. It's going to go to the correct direct jump. And so no matter what the size of the FLT, we're going to have the same 2 instructions or pseudo instructions. This translates well into assembly. I'm not going to go to the details. You can find these in the paper. So OK, we achieved all design goals. How well does this perform for an evaluation? So we evaluate against 5 MCUS applications. Pinlock is one we developed by our group. The other 4 are developed by STM Microelectronics, which is the manufacturer of the board. And we also compare, evaluate with the CoreMark benchmark, which is a standard MCUS performance benchmark. So first and most important is the security evaluation of our work. So we used pin lock, and just a background about this application, it mimics a smart door lock. So the user just enters a pin. This pin is hashed, and then we compare against a pre-computed pin. If it's correct, the door is open, the lock is open. If it's not, it remains locked. And so we assume a vulnerability in this function receiving the pin. The goal of this evaluation is not we're going to protect against CVE with number XYZ, but rather, is it possible to even launch a memory corruption attack on return addresses, or control flow hijacking attack on return addresses? So there are three possible scenarios that we can do here. First is a buffer overflow. So even though the attacker can overwrite the entire writable data, we actually do not have a return address in memory. We only have the state register, jump table, and sensor memory mapped I/O. So the attack fails. The second is an arbitrary write. The attacker can write to anywhere in memory, but there's no return address to write to. The state register is not memory mapped, it's never spelled, it cannot be overwritten. The jump table is in read and execute only memory, it's not writable. And the sensitive memory mapped I/O are protected through SFI, and again, they're not writable. The final scenario is a stack pivot. So the attacker takes control of the stack pointer and points the stack pointer to a vulnerable buffer, but this relies that, hey, we're going to pop a return address from a stack. But remember, the key contribution here is that nothing is pushed to the stack, nothing is popped from the stack, and again, µRAI protects against all control flow hijacking attacks on return addresses. Next, we have a secure design one to make sure that it's performant. And so we compare against the insecure baseline, and we protect, compare against a full SFI. The reason we compare against full SFI is that some defense mechanisms, like the safe tag, requires full SFI for its full protection. But as you can see on the bottom, for those in the back row who can see it, the overhead of full SFI alone is 130% overhead. However, for µRAI, we have only 0.1%. And the reason is that, if you remember, we only enforce SFI on a limited number of functions, which are the exception handlers and function called by it. And so that's the reason for our overhead, low overhead. We have an efficient mechanism to return, and we have limited number of SFI in our defense. So just to conclude, control flow hijacking on MCUs is a serious threat. Where µRAI secures against MCUs against control flow hijacking. We fully protect the return edge, the return addresses, but also all the evaluation that you saw is complemented with the forward-edge type-based TFI, so we have an end-to-end protection. We present a portable encoding scheme that does not require special hardware. We only need a general-purpose register and applicable to other systems, so it's applicable to other systems. We have low runtime overhead. The code is available at the following link, and I'm happy to take your questions.
Hi, I'm Aditya from Penn State. Good talk.
Thank you.
I had one question about indirect calls, which are decided at runtime. You can't, I guess, create such jump tables directly, right? At times, if you are creating an indirect call side. What do you do about that? You try to dereference all of them and create a jump table forcefully? Or have programmer practices so that they don't use indirect calls?
Thank you. That's a good question. So remember, we enforce type-based TFI. So let's say that an indirect jump can go to either function A or function B. What we do is that when we check what's the target, we use a different key for each of them. So if you go through function A, you're going to use a different key. If you go through function B, you use a different key. That protects the backward edge, but the forward edge is not protected by our mechanism. So our mechanism focuses on the return address only. But yeah, we make sure that the dynamic callers, we return to the exact dynamic caller.
Hi, thanks for the presentation. My name is Kai Ming from Penn State University. You mentioned the shadow stack and safe stack mechanisms in your presentation, and which they both have subtle limitations, which is that the detection for corruption or some bad things happened when the return address or some pointers got dereferenced. That is to say, if you have a return address got modified by the attacker, and you can't those mechanisms can't detect them from the real time when the modification happened. So I was wondering, this tool, return address integrity, do something about that? Real-time detection?
Yeah, so we basically combine. So conceptually, we do a shadow stack. So the problem with the defenses that you mentioned is that they have one of the three limitations: either limited security guarantees, requiring special hardware, or high overhead. Okay? And so safe stack, if you just use randomization, has limited security guarantees. If you use a shadow stack, it requires special hardware. It's impractical for these systems. Okay? So what we do is that we offer the same protection mechanism for a shadow stack with hardware, but we do not require all these constraints, high overhead or special hardware. I hope that answers your question.
Hey, Fabio from UCSB. How do you prevent me of crafting like a jump table in memory and then make like, I don't know, the return address point to that jump table, basically fake the jump table structure?
So we enforce depth. So basically we have the MPU. The jump table is read and execute.
If I craft another one like in another portion of memory and I point like the...
You need it to be executable. So we have depth in place.
Gotcha.
If you craft it, you basically write that jump table and then execute it. So you basically broke depth, right?
Yeah.
We enforce depth, so that doesn't happen. The goal of SFI basically is that you cannot disable the MPU to do your jump table.
Gotcha, okay. And another question, if I overwrite like some function pointer, like there are some objects in memory, overwrite those function pointer, how did you say you prevent that?
So we do not protect the forward edge. So if you have a function pointer that can go to either A or B, okay, you can still corrupt that. What we protect is the return address, when you return from the function. So if you corrupt that function to function A, we make sure that it's going to return to function A. You cannot return to the entire target set. So we basically protect control for bending on the backward edge.
Gotcha. And okay, thank you.
You're welcome. I'm happy to chat offline if that's not clear.
All right, let's thank our speaker one more time.